Welcome to this FuelSOME webinar. My name is René Itten. I am Senior Researcher at the Zurich University of Applied Sciences in the Life Cycle Assessment Research Group. And it is my pleasure to guide you through this third part of the webinar series on the FuelSOME project. The FuelSOME project focuses on a novel propulsion system for marine shipping that relies on the one hand on an SOC fuel cell based propulsion system, as well as new supply chains for synthetic fuels, including methanol, ammonia, as well as hydrogen. Today's presentation will be held by Alina Freino. Alina is researcher at Zurich University of Applied Sciences in the Life Cycle Assessment Research Group. She was responsible for the life cycle sustainability assessment of the FuelSOME system in the work package 4. And she will present the results of this work package. After this presentation by Alina, we will have a Q&A session. Please feel free to prepare or submit questions that we collect during the presentation of Alena so that we can ask them later. But now, without further ado, we move on to the presentation by Alena. Alena, please, the floor is yours.
Thank you very much for the introduction, René, and welcome also from my side to this FuelSOME webinar on Prospective Lifecycle Sustainability Assessment. René already quickly introduced myself, but again, from my side, my name is Alina Freiner. I'm a researcher at the Life Cycle Assessment Research Group at the Zurich University of Applied Sciences. So here, just a quick overview of the presentation outline. I will start with a short introduction to Life Cycle Sustainability Assessment, short LCSA. Then we will look at the motivation and decarbonization goals of FuelSOME. I will then introduce the databases that we used and the environmental and social indicators. And then I'll show you some results of the environmental and the social LCA. And in the end, we'll draw some conclusions and have the Q&A session that René mentioned. So, a short introduction into life cycle sustainability assessment. What is life cycle assessment? So let's start with just life cycle assessment, or short LCA. It is a standardized method that allows us to quantify the impacts that a product, service, or process has on the environment and on human health. And more specifically, what LCA does is it takes into account the environmental impact of a product throughout its entire life cycle. We call this cradle to grave, so from the very beginning to the end. A life cycle usually starts with the extraction of raw materials that we need in order to produce our product, for example. Then the second stage is the manufacturing of the product. That is usually followed by some transportation, for example, by airplane, ship, train, or trucks, or all of the above. Then we have a use phase where the product is being used, and in the end, we have some disposal and or recycling activities. Where is LCA usually being applied? So it's often used for comparisons or benchmarking of various products. So we analyze a product and we can then see what are the impacts on, for example, the environment. But what we want to do usually is, of course, put that into context, compare it to similar products, or use it for benchmarking. What we also often do is weakness analysis. So if we analyze the life cycle of the product, we can then also analyze, for example, environmental hotspots and see where most of the impacts arise. It can also serve to identify data gaps or methodological uncertainties. LCA is also used in strategic planning or for eco-design and product development. So once we have identified, for example, our environmental hotspots, we can then use this to optimize our product, adapt its development according to these findings from the LCA. This is relevant for operations management, where environmental or also social factors can be integrated into decision making, which is also important for legal decisions, where LCA can be used as a tool for decision support, and it can be used in communication and marketing. For example, eco-labels or just product information, where this LCA information can be used to create more transparency. A life cycle assessment is divided into 4 phases, and that is also standardized in accordance with the ISO standards that are here mentioned. So the first phase is always the definition of goal and scope. So here we define our objectives of the LCA and we define the scope of our study. So the product system, what processes are included and what processes are excluded. The second phase is the life cycle inventory, so our data collection phase, where we gather our data and we also model it. In the third phase, the life cycle impact assessment, we then assess our data. So we apply impact assessment methods and generate the results. And in the fourth phase, the interpretation, we interpret the results, we analyze uncertainties, and we draw conclusions. Now, and let's say extension to LCA is LCSA, so the Life Cycle Sustainability Assessment. And the LCSA aims to provide a holistic understanding of not only the environmental, but also social and economic implications of the product in question. So it includes these 3 key dimensions: the environmental impacts, which is called ELCA, the social impacts, which are analyzed with SLCA, and the economic impacts, which is assessed with a TEA, that's short for techno-economic analysis. So they are being carried out as 3 separate assessments, but it is very crucial that we ensure that the goal and system boundaries of those 3 assessments are well defined and aligned, so that in the end we are able to bring them together, compare them, integrate them, and analyze them as one whole picture of sustainability. Moving on to the motivation and decarbonization goals of FuelSOME. Regarding the shipping industry, it is globally responsible for 3% of CO2 emissions and 20 and 12% of nitrogen oxide and sulfur dioxide emissions, respectively. In addition to that, the global shipping industry is consistently growing, so the mentioned emission levels from international shipping will continue to increase in the coming years. Marine shipping is also considered a hard-to-decarbonize sector, and that is due to a few different reasons. For example, there is a high energy density requirement. So we have this need for alternative fuels, but they need to be able to fulfill a high energy density. Another challenge is the refueling infrastructure, which is in place for the conventional fossil-based fuels, but for the alternative fuels, that is a different story. There's also the aspect for cost and competitiveness, as well as technical challenges. This is where FuelSOME comes into play, and it aims to contribute to this need of alternative fuels and finding a way of a sustainable supply of specifically ammonia, methanol, and hydrogen at qualities that are suitable for maritime application and that are also capable of being used at scale. Regarding the decarbonization goals, those are in line with the International Maritime Organization, or short IMO, which is the United Nations specialized agency that is responsible for the safety and security of shipping. In 2018, IMO set environmental targets to reduce greenhouse gas emissions by at least 50% by 2050 compared to the 2008 emission levels. This year, so in 2025, IMO set new targets and they approved net zero regulations for global shipping by 2050. But since the FuelSOME objectives were set in 2022, they remain in line with the reduction targets that were set by IMO in 2018, so this 50% reduction in greenhouse gas emissions by 2050, and that is also what we refer to when we assess our results. Also in 2018, IMO published LCA guidelines, and within the FuelSOME context, we try to stay in line with those guidelines. And what IMO states in these guidelines is that they adopt an approach that is consistent with an attribution LCA, as they aim to describe the environmental impacts of a defined system rather than modeling broader market consequences. So for our analysis in FuelSOME, we also adopt the attributional LCA approach. So these are the specific objectives of our work package, which is the techno-economic analysis and LCSA. So within our work package, we aim to carry out and evaluate the technical and economic feasibility of the FuelSOME system, as well as identify the environmental and social benefits that this new propulsion system can have. We further want to compare the environmental, social, and economic sustainability performance of the FuelSOME system to conventional alternatives. And specifically for our task, we also want to identify the environmental and social hotspots of ammonia, methanol, and hydrogen e-fuels for this system. So regarding the databases that we used and the environmental as well as social indicators, for the eLCA, so environmental LCA, we used the EcoInvent database. It is a unit process LCI database with a high resolution as we are working with process-based LCI data. And for the social LCA, we used PSILCA, which are multi-regional input and output data that represent global supply chains. So here the resolution level is a bit lower as we are working with sectorial resolution. We also worked with Premise, and what Premise does is it modifies the EcoInvent database in such a way to reflect future policy scenarios based on integrated assessment models. There's a number of different models, and the one that we used is called REMIND, which you can see here. REMIND stands for Regionalized Model of Investment and Development, and it combines macroeconomic growth, energy system, and climate policy analysis. In this map, you can see the different regions that are covered in REMIND. So you can see it covers the whole world and has pretty much one region for Europe. So since FuelSOME focuses on the European region, this was the most useful for us as we can consider Europe as one region. Then within the REMIND model, we have different scenarios that you can see in the colored lines in this graph. So we can see different SSPs, which stands for Shared Socioeconomic Pathways. So these are just the different socioeconomic pathways that our society may take in the future. And we decided for the SSP2, which is the middle of the road scenario. So here we assume that the world follows a path in which social, economic, and technological trends do not shift considerably from patterns thus far. So it continues in a similar way. And from the different scenarios that you can see, we then chose 4 different ones that are highlighted here in order to kind of show the range of scenarios. So at the top, you can see the NPI scenario, which is the most conservative one. It stands for National Policies Implemented, so it assumes that only currently implemented national policies continue. And it's in line with about 3-degree warming. Then the second most conservative one is the NDC, so Nationally Determined Contributions, which aligns with about 2.4-degree warming. And then we also considered peak budget 1,650, which are more strict climate scenarios where the remaining global carbon budget is 1,000 or 650 tons of CO2 respectively. And the 1000 budget aligns with a below 2-degree warming, and the 650 budget with a around 1.5-degree warming. All right, so regarding the environmental and social indicators that we applied, for the environmental analysis, we used the greenhouse gas emissions according to the IPCC method. We also analyzed particulate matter emissions and marine eutrophication and some others, but those are the ones that we will be showing today. And regarding the social indicators, you can see here is a list of all the indicators that you can assess using PSILCA. So this is a very, very big list of indicators. And today I will just show one example indicator to get an idea. And then let's look at some of the results for the environmental and social LCA. So I'll first want to show you the system boundaries that we considered for the LCAs. So here you can see at the bottom in the colors the different life cycle stages that we considered, and the first one in blue is the feedstock production. So since we're focusing on e-fuels, you can see here the different electricity sources, so PV, wind, and so on. Then we have the fuel production and the fuel processing stages where the ammonia, methanol, and hydrogen are being produced. We also have the production of the propulsion system itself, which is composed of different components such as a processing unit and the SOFC stack, so the solid oxide fuel cell stack, which I'll go into a bit more detail in a minute. Then we have a use phase, so the operation of the maritime vessel, and in the end we have the disposal of the propulsion system. The functional unit is defined as 1 ton-kilometer transportation of a maritime vessel with a power output of 10 megawatt. This is an overview of some of the assumed efficiencies. So you can see the electric motor and converter efficiencies are consistent across the 3 alternative fuels. Then we have an SOFC, an electrolysis efficiency that is based on project internal information. So the SOFC efficiency for ammonia is at 49%, at 44% for hydrogen, and at 53% for methanol. And the electrolysis efficiency is at 70% for all 3 fuels. And at the bottom, you can see some synthesis efficiencies for the synthesis of ammonia and methanol, respectively. All right, so regarding the solid oxide fuel cell, we modeled a detailed and project-specific SOFC stack, which was built and tested by a partner in the context of the FuelSOME project. And here you can see some of the most important SOFC stack properties. So for example, you can see that the rated nominal power of the stack is 3 kilowatt, and the efficiency of the fuel cell as well as the stack is at 75%. The nominal life expectancy of the stack is above 45,000 hours. So looking at the greenhouse gas emissions of this SOFC stack, you can see that in total it comes up to 1.6 tons of CO2 equivalent for the entire stack. And looking at the contributions, we can see that 65% of the greenhouse gas emissions of this stack is caused by the fuel cell production, here in orange. And within the fuel cell on the outer ring, you can see that the electricity consumption in order to produce this fuel cell is responsible for 80% of those emissions. Then aside from the fuel cell production, we also see that the electricity consumption that is used to produce the stack itself contributes another 17% to the overall greenhouse gas emissions, and the steel contributes 9%. So in total, the main driver of the emissions here is the electricity consumption that totals up to 71% of overall greenhouse gas emissions. Okay, here you can see an overview of the results for the environmental LCA. So at the top, you see the 4 different premise scenarios that I introduced to you before. And we analyzed them for 2 different time horizons, which are 2035 and 2050. And we are here looking at 4 environmental indicators, which are greenhouse gases, marine eutrophication, particulate matter, and mineral resources. And we have different scenarios of these alternative fuels. So for each ammonia, hydrogen, and methanol, we have a conventional fuel pathway, and then we have 3 e-fuel scenarios, one with the ENSO mix, and then PV power and wind power. The numbers that you see are relative to the fossil reference, which in this case is a maritime vessel that is operated with heavy fuel oil. And you can see the more blue the numbers get, the more the impacts are reduced compared to this reference case, and the more red the numbers get, the more the impact increases compared to the reference. So for greenhouse gases, for example, we see a reduction for most of the alternative fuel scenarios that we're looking at. And especially we see that the hydrogen shows the highest decrease in impact compared to the fossil reference. And we also see that the PV and wind power scenarios show the lowest numbers. The same goes for marine eutrophication. We also see here it gets even more blue, which means the impacts are decreased even stronger compared to the fossil reference. And again, for the hydrogen, they show the lowest impact on marine eutrophication compared to the fossil reference. And also for particulate matter, the decrease is a little bit less strong, but still we see lower impacts or lower emissions of particulate matter for most of the alternative fuel scenarios compared to the fossil reference. Now what we see is a trade-off. So for 3 of these indicators, we see that the alternative fuels show lower impacts for most cases. And when we look at the mineral resource use, we see a very strong increase. So if we compare it to our fossil reference case, we can see that all of our alternative fuel scenarios have a much higher mineral resource use compared to the fossil reference. And that we can also especially see that also the PV and wind scenarios show a strong increase. So in order to provide this renewable energy, we need the infrastructure for it, and this uses a high amount of mineral resources, which then explains these higher impacts compared to the heavy fuel oil. Now looking at just the greenhouse gas emissions again, we can see here a contribution analysis. So we chose just to show the NPI scenario, which is the most conservative one of the premise scenarios that I showed before. And we again have the same fuel scenarios that we just saw. So we have the heavy fuel oil reference. We here also have liquefied petroleum gas and methane. And then again, the different scenarios for ammonia, hydrogen, and methanol with the conventional pathways, as well as these 3 e-fuel scenarios. And the results are indicated in kilogram of CO2 equivalents per ton kilometer. And again, what we can see is that the e-fuels from wind and PV power show the strongest reduction compared to the fossil reference. And we can also see that for all of the 3 alternative fuels, those scenarios that are based on wind and PV power reach this reduction goal or this decarbonization goal of 50% reduction of greenhouse gas emissions. We also see that the e-hydrogen shows the lowest impacts compared to all other fuel scenarios. And we see that it has slightly lower environmental impacts or greenhouse gas emissions compared to e-ammonia, and quite considerably lower impacts compared to e-methanol. And why that is the case is shown if we look at the processes that explain this impact. So as we see that all e-fuel scenarios are dominated by the fuel production, which are the blue shades that you see in the bars. And if we look, for example, at ammonia, aside from the e-hydrogen production, we also have some impact from the heat input, as well as the nitrogen that is needed for the synthesis of ammonia. So that explains some of the difference why the e-ammonia has higher greenhouse gas emissions compared to hydrogen. And in the case of e-methanol, we see this additional input of CO2. Here we assumed CO2 from a cement plant. And as you can see, the lower the overall greenhouse gas emissions get, the more relevant this CO2 input becomes. So it is very relevant to consider where is this CO2 coming from if we are thinking about the methanol case. Okay, so as an insight into the social LCA, I want to show you the social indicator of fair salary. And here you can again see the same scenarios or similar scenarios that we just looked at before. So we also have this conventional scenario of heavy fuel oil as the fossil reference. And then we have the three alternative fuels, again with a conventional pathway where it's being produced with natural gas in this case. And then we have also e-fuels from PV and wind power. The results are indicated in medium risk hours per ton kilometer. And when we look at the contribution or how the e-fuels perform compared to the fossil reference, we can see that the e-fuel scenarios are associated with slightly lower social risks compared to the reference case. However, this decrease is not as strong as we just saw in the environmental analysis. Then looking at where do most of the social risks arise, we can see that they mainly arise in terms of fair salary during the ship operation. So this is considered equal across all fuel scenarios because it only concerns the operation of the ship and not the fuel production pathway. And that is what dominates the social risks, in this case, the fair salary. Then the remaining social risks in the e-fuel scenarios is how we can see explained by, or they arise in the respective electricity sectors. So for the PV case, for example, we can see that the electricity sector of PV has quite a relevant contribution, as well as the wind or natural gas, depending on what scenario we are looking at. All right, so to draw some conclusions, we saw that the social risks primarily arise during the ship operation, as well as in the respective electricity sectors, depending on the electricity source that's being used in the e-fuel scenarios. Then regarding the environmental performance, for the e-fuels, we saw that the energy source that's being used for the electrolysis is crucial. And we also saw that wind and PV energy generally show the lowest environmental impacts. We also saw, however, that there are some trade-offs between the different environmental indicators regarding especially the performance of the e-fuels. So we looked at greenhouse gas emissions, and we saw, for example, a strong trade-off with mineral resource use. And lastly, we also saw that among the alternative fuels analyzed, hydrogen generally shows the lowest environmental impacts. To conclude, we can state that in order to substantially decarbonize the shipping sector, the ships need to be powered using either hydrogen or ammonia ideally, and they need to be produced from 100% renewable energy. Thank you very much for your attention.
Perfect. Thank you very much, Alina, for this very insightful presentation. Yeah, now it's time for the Q&A. We already received some questions for the Q&A session, but still, if you want to add further questions, please submit them now. The sooner you submit the questions, the more likely it will be that your question will be answered. So, but now starting with the questions, we start with some questions of understanding. And then one of the questions was, can you explain what are medium risk hours?
Yes, of course. So let me just go to Oh, I had a slide, but I don't know if it shows. Um, Medium risk hours represent the number of working hours that are associated with a certain social risk and over the entire life cycle of this product, and that is defined in the PSILCA database. So what PSILCA does is it assigns risk levels, which go from low to very high, and it assigns them to social indicators, like for example, we just looked at fair salary, or it can be child labor, or many more. And those risks are country and sector specific. So the labor time from the life cycle inventory is linked to these risk levels, and that's how the medium risk hours are calculated.
Okay. Good. Then another question was then what kind of software did you use to perform all these calculations of the results that you presented?
So for the environmental LCA, we used the CIMA-Pro software. And for the social LCA, we used OpenLCA with PSILCA. And we also then worked with Premise, and we also used CIMA-Pro to work with Premise as we imported those databases and were able to make our analysis within CIMA-Pro.
Okay, and moving on, in the beginning you mentioned like the economic dimension is also part of the analysis, but you did not show any results on this. So yeah, what about the economic dimension?
Yes, so as I just mentioned briefly, the environmental, social, and economic dimensions are all being carried out as separate assessments, and we from Zurich University of Applied Sciences are responsible for the environmental and social assessments, and the techno-economic analysis is being carried out by a different partner within the FuelSOME consortium. So they are for now carried out as separate assessments, and then in a last step, these three assessments will be brought together um, in order to have this picture of sustainability as a whole.
Then another question is, how did you decide on for which indicators you want to focus on? Because you only showed results for selection of indicators.
Um, yes, so we did and will analyze more indicators. Of course, I can't show them all here, but we just decided on some of the most relevant indicators in a maritime context, so for maritime shipping. Of course, greenhouse gas emissions are always relevant, as well as particulate matter emissions. And since we are talking about a marine application of this propulsion system, marine eutrophication is another relevant indicator. Um, so those are just some of the most relevant ones that we now decided to show. But of course, it's important to try to show the picture in a most comprehensive way possible in order to also be able to show those trade-offs that we were already able to see with just the three indicators that I showed. So we tried to show them all and tried to show the trade-offs between one another um, in order to, to make statements for the sustainability as a whole and not limit ourselves to just the carbon footprint, for example. And the same goes for the social assessment.
Okay. Okay, yeah, thanks for this comprehensive answer. Then another question was you described this premise scenarios, and these are quite comprehensive and far-reaching into the future. How confident are you about the reliability and the robustness of these scenarios that you used for the prospective analysis?
I mean, of course, they are um, prospective scenarios, so we are working with assumptions. It is just a projection of how society and also the emissions levels could develop in the future. But I think what we tried to do with also these four scenarios that we chose is we tried to show the range. So of course we don't know exactly where we are going to end up with, but showing a range kind of shows probably in between what numbers we could end up in. So that's also why we picked a very conservative scenario, then quite an optimistic one. And I would say we can somewhat confidently say that it will be somewhere in between there. Of course, that's a large range still as well, but it at least gives an idea of where we could end up at roughly.
Mhm. Then another very interesting question, I think, is you mentioned that I think it's 3% of the greenhouse gas emissions come from marine shipping, and so it's a lot of greenhouse gas emissions. And if we want to decarbonize this fully, uh, how large will the electricity demand be if we move to e-fuels or synthetic fuels for the whole marine shipping industry?
Yeah, that's a very good and relevant question, of course. We did make a calculation on what that could roughly look like, just based on how big is the worldwide fleet today, how much fuel is being used at the moment, and what is therefore the energy requirement that needs to be provided through either heavy fuel oil, or in this case, then alternative fuels of ammonia, hydrogen, or methanol. And calculating this down for all three alternative fuels showed that it would about be 30% of the annual global electricity consumption. So this is, of course, a very high number, and as we also saw, it cannot be just any electricity source. If we have those decarbonization goals, we need to focus on renewable electricity, and if we are speaking, 1/3 more of what is globally being consumed today anyway, of course, that is a huge number, and will be difficult to, let's say, fuel the entire world fleet with e-fuels. That's, of course, talking about a very big amount of electricity.
Okay, yeah, then I think we are approaching the end of the Q&A session, and again would like to wrap up with two personal questions, or two questions for me. And for me, Alena, what was for you personally the most surprising result of this comprehensive analysis and study that you performed?
Um, the most surprising, I would say, is how big the trade-offs are. So we see, like I showed before, in some indicators that we're looking at, or some aspects that we assess, we see a very extreme improvement if we use these alternative fuels, and especially the e-fuels. And then in other indicators, we see a very, very extreme um, increase in impact. So I think the range of these trade-offs surprised me, and like how large they are. So it's not really in the end easy to say what is better and what is worse, but we really need to weigh and look at the whole picture in order to be able to make a conclusion in the end.
Hmm. And then for the last question, which option would you choose if you had to decide on yeah, how you want to fuel the maritime shipping sector in the future?
As a whole, I would say it would probably have to be a combination. We did see in most of our analysis that e-hydrogen, can be very beneficial in a lot of indicators and a lot of aspects. But I also think that fueling the entire world fleet with e-hydrogen is just, as per today, not very realistic. So I think the best option would probably be to opt for a combination in some way of integrating, for example, e-hydrogen or also e-ammonia as a fuel for maritime vessels, but not limit to just one single option, I would say.
Okay, yeah. Then with this, we are at the end of the Q&A session. Thank you very much, Alena, for the presentation as well as the answers on this many questions. And also thanks for these interesting questions to the audience. Furthermore, I would like to thank Albert and Kerstin from the AVL support team that supported the technical side of this webinar recording. Yeah, this webinar is part of a series, so it would be my pleasure to welcome you also in any of the other webinars on the FuelSOME project.